Hi, listeners, and welcome back to the ALD Stories podcast. Longtime followers of the show may get a bit of deja vu with this episode, as we excitedly welcome back our very first guest on the show from episode 2, Riikka Puurunen. Riikka has the distinct honor of being our first guest to be featured on their own second episode, although superfans will know that Jonas Sundqvist was the first to be on twice. I joined Riikka at her home campus of Aalto University in Espoo, Finland, just west of Helsinki, where we were lucky enough to take advantage of Aalto's beautiful recording studios in the Harald Herlin Learning Center, just one of the many resources available to the university population. Riikka is a professor in the Department of Chemical and Metallurgical Engineering, where she's the head of the catalysis group. At Aalto, she continues a rich ALD and nanotechnology pedigree, joining the faculty after many years of working with Micronova, a laboratory jointly run by VTT Technical Research Center and Aalto, which focuses on nanotechnology, material device physics, and optics. In addition to her lab work, Riikka also kickstarted the virtual project for the history of ALD and is a champion of open science and learning. I know few people better suited for featuring on ALD stories. In this episode, Riikka and I take a deep dive into the topic of conformality, a property of ALD that many of you are surely familiar with and for which some of you rely on for your work. Riikka has published and collaborated on many projects aimed at understanding conformality in ALD and even created the PillarHall test structure, lateral trenches aimed at screening the conformality of ALD processes. We chat about the history of conformality in ALD, recent findings in conformality modeling, the origins of the PillarHall test structures, and end with short discussion on open science. I cannot thank Riikka enough for her hospitality at Aalto and continued willingness to contribute to this program. Please be sure to check the description for links to all the wonderful projects Riikka is spearheading and consider making a contribution yourself. So with that, grab your tea or coffee and please enjoy episode 14 of the ALD Stories podcast.
Welcome to ALD Stories, a series of conversations where we share the untold stories of atomic layer deposition and the people behind the technology. This podcast is brought to you by Venek, the home of ALD.
Welcome everybody to another episode of ALD Stories. I'm here with Riikka Puurunen at Aalto University. Riikka, thank you again for joining us again on ALD Stories.
It's an honor.
Yes. I think we have to get a couple of things out of the way because there are things that are a little bit different on this episode than some of the past ones. First, it's not the first live episode that I've done, but it's certainly the first one in a actual studio. We're here in the, and I don't remember the name of this. You refer to it the
self-service studio Aalto something. Yes.
Yes, and we have the nice little Aalto symbol here on the front, and we are in the the Harald Learning Center?
Harald Herlin Learning Center.
Okay.
This used to be the library.
Okay.
Yes.
So yeah, we have a very professional recording studio here. And then second thing is you are not the first person to come back on the show, but you are definitely the first person we have having your own episode. So congratulations. It's an honor to have you here a second time.
Thank you. I'm very happy for this invitation, and the topics today are going to be interesting.
Yes, they definitely will. And so I think we can jump right into it. The topic that we're going to talk about mainly technically is conformality, which I think everybody has some kind of familiarity with it, or at least if you're listening to an ALD presentation or podcast or whatever it is, you probably have some idea of conformality, but maybe you can walk us through why conformality is so important. What does conformality mean for ALD, and how has our understanding of it changed since the kind of initial conception of ALD to now?
All right. So there were lots of questions there.
Yes.
So conformality, what does it mean? Well, first of all, it means that when you have a complex three-dimensional structure, when you grow a film on that, you coat all places with the same kind of a film. People think of the same thickness usually, but I tend to also associate the assumption that the film has the same kinds of properties. So not just the thickness, but also the composition and so on. And that is very important for some applications. It was not so important in the beginning for ALD.
Really? Okay.
To my understanding, there was not much attention to that in the very beginning. So if we talk about the Suntula originating ALD or atomic layer epitaxy, and then the St. Petersburg group originating ALD molecular layering, I don't think that I've seen any discussion really about conformality in the early papers. So For the Suntola work where the electroluminescent displays were the target, well, they are planar things. So there, Suntola was thinking more of a high quality of the film.
Okay.
But what you run into there is you also need to have pinhole-free films for those devices to work. And that's actually where also conformality has helped, I think, because there is this notion that at least went through in the thin film world. I was working with at Micronova and film films for a while, that ALD films don't really have pinholes, because if there would be particles, they are lifted up when the film grows. So the film grows also under the particles. So that's kind of a notion of conformality, I would say.
Okay, yes.
And then thinking of the St. Petersburg group, they were working with powders in the beginning. I assume that they have been like maybe some hundreds of micrometers of size. I'm not sure, but high surface area powders. Sure. I don't recall seeing in their papers discussion about conformality, but maybe they assumed it, that it comes, that the coating is uniform, because it should. If you have these reactions that are saturating and irreversible or self-terminating or self-limiting, as people like to say, it should come automatically when the doses and times and so on are sufficient. But the first time that I know that conformality has been like raised as an issue is from the 1994 MRS conference in Boston, where Suntola and microchemistry were presenting, and in the history atomically epitaxy history essay that I wrote, there's also a picture of what they were presenting there. So that's like a step coverage picture. That was really impressive then, Suntola told. It's not very impressive to us at the moment, but that was already significant to raise the interest of the companies at that time. And then, well, after that, maybe you might remember, or the listeners might remember, a Ritala et al. Paper from 1999, I think, where there was a trench picture that's quite famous, but it was not a very demanding one, maybe 5:1 aspect ratio or so. And nowadays, of course, we are doing 100:1 or 1,000:1 or 10,000:1. I think that the record might be over 50,000:1 already. I think so.
Okay.
Yeah.
Deep and thin.
Yeah.
That's really interesting. So the idea of conformality, maybe to the initial inventors, was just this implicit characteristic of ALD that didn't need to be explicitly said. That's okay. If you are looking at it, you'll understand that it should be conformal, and didn't require any initial discussion about it until somebody really cared.
Well, yes, and the need for conformality came later with the microelectronics, when the deep trench structures started to evolve to have the high area for capacitors and so on. I think that's what it's related with. So in 2003, I think that the first DRAMs went to market with ALD, or maybe 2004. I'm actually not fully sure of that. And then for the memory chips, the 3D part came a little bit later. So first, those were also just planar things.
Was there any discussion back at that time kind of towards these types of applications, that they were having some thoughts of, the conformality might help us in some way in the future, or were they really just kind of focusing on the planar aspects of it because that was what was necessary at the time?
You are talking about Suntola and 1980s, are you? I was like 10 years old. I actually don't really know, so you should maybe ask Suntola to be on your show.
Yeah, that's very interesting, because I think right now we talk about conformality all of the time. At least in our applications that we work on at Bennick, we talk about conformality almost constantly, because that is almost the most important aspect of ALD for a lot of the emerging applications that we're looking at. So the idea that it wasn't much of a discussion when it was first happening, I think is very fascinating, at least from somebody who just started doing ALD less than a decade ago.
I guess that is the stronghold of ALD. That's why people would use ALD nowadays. Like, ALD still has the name that it's slow and expensive. But so if you can do the thing with something else, you do it with something else. But if only ALD can do it, and that's the conformality aspect there is really special. It's if you look at the other thin film deposition methods, they cannot compete. The physical paper deposition and CVD up to a certain point, but not I think 50:1 aspect ratio also is the limit that you would expect.
Is the definition of conformality or our understanding of it different now than when ALD was first kind of conceptualized? Is conformality still kind of the same concept, same idea?
Oh, that's a good question. So when would people have used this word for the first time? I've looked at the history of many terms, but not conformality. So I would not know when it emerged, actually.
Okay.
But when we were writing the review article, for example, with the University of Kent people, so Veronique Kremers and Jolien den Doven, we also made these simple schemes and discussed a lot. So the word conformality it's actually not something that's well defined. You then need to define what you talk about. Do you often people talk about step coverage? That's better defined. But to talk about conformality, you should define like what's really the measures. Are you talking about the ratio of film thickness at the bottom of a feature to the planar surface or some sides or something else? Or then with these, we'll talk about the PillarHall test structures later, and there it would be, these are so demanding that it would be more natural to talk about penetration depth, or we have been using the 50% thickness penetration depth or half coverage penetration depth, how you want to define it. But just as a measure how deep the film actually grows, because there the structures are typically so deep or so long that the film does not grow to the end. They have been made like that.
If there are any linguists or language enthusiasts, maybe I'll look up the etymology of conformality or conformal. I can put up the definition here.
That would be
on the
interesting.
bottom.
Yes,
I'll put it right here next to the Aalto.
thank you.
It's like a little chalkboard, I think.
Oh yes,
a little chalkboard for text for us.
Oh, indeed.
Yeah. Okay. So, hey, I think you mentioned just when we first started talking about this that conformality doesn't necessarily have to refer to just the thickness. It can also refer to the properties of the film. And these are a lot of parameters that can go into this. And because it's such a powerful parts of ALD, is it an inherent property of ALD? Just doing ALD, is that to mean that it will be conformal? Or do we have some tweaking and some knobs that we need to turn in order to actually get conformal films out of the process?
That's a good question. So people like to use the word ideal ALD. You see it a lot in papers, and usually people don't define what they mean with that. And I think that the definitions vary a lot. But how I see it as ideal ALD, it would be if you have the reactions that are saturating and irreversible. That's for me sufficient to be ideal ALD. So no requirement of a full monolayer growth per cycle. I hope that everybody has already abandoned that, but you see it a lot in papers still. So if we would have these self-terminating reactions or saturating and irreversible, and they are separated perfectly, then the conformality would follow as a natural thing if the dose is sufficient. So it will depend on what kind your 3D structures are. So if the aspect ratios or if they are very demanding, then you will need to tweak the process indeed to be able to allow the molecules to diffuse actually to the bottom, and also to provide enough so that all the sides are covered. So that's a yes and no answer in a way. But then there's also the other side that the ideal assumption, it really requires that there's no side reactions such as thermal decomposition of the reactants. And that would, I guess, be the most typical, that you have a little bit of a CVD component there, so a continuous growth component in addition to this purely saturating one. And if you have that, then you would not be able to get that fully conformal film, because while you are filling the 3D structure, then you will have like a continuous growth more at the opening of the feature. And that's challenging to know whether that takes place if you don't have the experiments made, and they are not really made that much yet, I think. So the experiments on just thin films might not sensitively show this little composition of CVD, I think. So I think that when, for example, looking at the processes that have been tabulated in the review article, Mikkulainen et al. 2013, and that was converted to the ALD database with some added things and updates from the atomic limits system and the University of Eindhoven. So the way those processes have, I started putting them up in that table for the 2005 review, and I included everything there. So if the author said that it's ALD, I have included it. So that's not a critical review. So there will be lots of processes there that actually have a significant CVD component, I think.
That we just didn't have the technology or the thoughts of how to measure what the CVD was or the components of it.
Yeah, and people have wanted to publish under the name ALD a lot of things. Yeah.
So as much as of a misnomer as ideal ALD, maybe conformality should follow as long as we give it sufficient time for the most parts.
When our choice of reactants is correct, is proper. Some people want to call them precursors. I've stuck with the word reactant for a long time, and that's also in the ALD database. So I use those terms interchangeably.
I think that we've seen in the past few years that ALD is not as simple as the picture that we make it. There are loads of other things that can happen, side reactions, all of these types of things that kind of deviate away from that ideal ALD that we like to talk about, and the pretty cycle picture that we like to put up. Has conformality been something that was looked at a lot in the past, or did we just kind of breeze by it and say, okay, if we do a little bit here, then this film should be conformal? Or is it something that people are like, okay, we should really, really understand how to make a conformal film, like a truly conformal film? Or did we just like, okay, if we're doing ALD, then it should be conformal enough?
I think you find both approaches in the literature. There are great papers really examining the conformality already from 20 years ago. The Gordon et al. Paper, for example, with a very, very simple modeling part and also experiments. That's an example. Then there is a paper also by, I think, Jeff Elam is the first one, about, maybe anodic alumina or something. They have done really great work to look at how the conformality evolves. And so there is this aspect in the scientific literature, but then there's also lots and lots of papers that claim it's ALD, it's conformal, and that's it. Okay. They make the conclusion just because they claim it's ALD.
Right, we can see the growth rate per cycle is linear. Like, okay, there we go. There's our ALD. Perfect.
Yeah, and I could criticize that one also. Growth per cycle linear with number of cycles. Well, if you do pulsed CVD, you get that. So that's not a proof of ALD of any kind.
Well, I think that's a good segue then into a recent paper of yours concerning conformality, and I was also working with some models, but all the details I will let you discuss. I think that's not my place, but maybe you can just give a quick overview of what the idea of this recent paper was.
If you allow, I'll refer to two recent papers.
Yes, please.
Because one was it got its volume number and page numbers just, I think, yesterday I saw them.
Great.
So there are two papers. They are in physical chemistry, chemical physics. And the first one is actually an experimental study. So there we used those PillarHall test structures. So these are, we call them lateral high aspect ratio structures. So they are, normally people have been, or earlier people used the vertical trenches to look at, or holes, to look at how the film grows. But we tilted them, made them horizontal and very, very long. And in that paper, we used those to look at the trimethyl aluminium water process, so the TMA water, the conformality of that, and also varying the gap height and the film thickness and so on. That's really I would say a very basic paper on the topic, and related to these developments. When I was still working at VTT, we also wanted to model those. So I had a colleague, Markku Ylilammi, who actually did his master's thesis for ALD in the 70s. Mm-hmm. He's one of these really
the originals.
long career guys. Yes, but he hasn't worked with ALD all the time. He worked other things, but he then took up the challenge to develop a model for us to be able to also simulate the conformality and to understand better how the experiments go. So he typed in the model, and it's used in also there's this Ylilammi Riikka Puurunen paper where the model is introduced. We didn't get the code, so I moved to Aalto University, and the code actually was left at VTT. So a student at Aalto typed it up again. A summer student who is now a doctoral candidate.
Great.
Chemical and process engineering masters. They know MATLAB and modeling, some of them very well. And she was able to write it up. And we have used it for simulations in both papers. So also with the experimental one, just to show that we get similar trends. And then we have just now a recent paper where this Emma Verkama, who typed it up, is the second author with the equal contribution, where we use the model to simulate all kinds of cases which we can think that are realistic to people who are making experiments. So to better understand how varying individual parameters actually affects the conformality. Mm-hmm. So we've learned a lot ourselves from this. Many things are so complex that we just by seeing the equations, it's difficult to really picture how is it going to affect things in practice. But now we've simulated lots of cases, and because of this experience of the code was there and then we couldn't use it, we are actually going to publish the code. Okay. We are in the process of doing that, but it's not a fast thing. We want to make sure that it's good, and we can be proud of the code when it's published. So I hope maybe before the ALD conference it's going to be out. I hope so.
Yeah, I think this is going to be coming out around the time of the ALD conference. I was just thinking, okay, do I need to do a disclaimer that this was recorded months months ago?
Yes, you should.
Yeah, I think I will have to. Oh, but that's okay. So how does that process go of rewriting a code? Is it just, okay, I have some outputs and I know the general idea of how this code is working, so I'll fill in the gaps? So
all the equations are in this Ylilammi et al. Paper that's in Journal of Applied Physics. So that's of course the basis. And then this Emma pondered for some time. This was an extra side project for her summer job. I gave her the challenge, would you be able to? And I looked at it, and I think maybe in 2 weeks or so she had it written up. So it's written with MATLAB and 3 different scripts that, one is the main one that is running the other ones, and then comparing if you get the same results and finding out an error in one of the equations, and that was the hardest thing.
Okay, that's fantastic. I did a little tiny bit of coding during grad school in MATLAB, and it was horrendous. I don't have any envy, just a lot of respect for those that can do it. So,
and the beautiful thing is that once somebody who knows how to code does it, then others can use it.
So this is great. This is in the new paper you just said. I got the page numbers and volume that this will be published
so there we were using the model to simulate all kinds of cases. So the code that's the basis of that paper will be published.
Good.
Yes, and also some of the data, but that also takes some time. So, and it's not really rewarded by any direct means. That's why this is also remaining too easily as a side project. But I think that for the advance of science, that's actually really important. Advance of a scientific field.
Absolutely. So I've read the paper that has not or was published already. Of course, I haven't read this one yet, but in the conclusions there, there were some obvious things or things that we already know that affect kind of conformality. That's okay if you increase the pressure, the penetration depth goes further, but you'll still get the same thickness. These kinds of things. What were some of the maybe more unique things that you saw when doing this modeling that we haven't had too much discussion on before?
Yeah, indeed. So there's lots of papers that report on the effect of dose. So partial pressure times time. And of course, those assume that you always have the same partial pressure at the beginning, which is also not necessarily true. So lots of simplifications there. But for example, one mystery to solve was it's actually completely logical then when it's solved and you think of it, the effect of growth per cycle on the conformality, on the penetration depth. That actually, when you have what some people would say a better ALD process, more effective one, where you have a higher growth per cycle, that's going to go less deep into the high aspect ratio features. It is because the surface consumes so much of your molecules. So you are putting in the same dose. But if we call it the adsorption capacity of the surface, if it is high, let's say 5 some payload metal atoms per square nanometer. This is Sean Barry's term, or somebody's before him, payload atom, so the metal atom. I like to think in these terms, by the way. So atoms per unit surface area. This is something I learned from Suvi Haukka and Tuomo Suntola and so on. So if that's, let's say, 5, that would be half a monolayer of the film to be grown or something, so realistic value. Or if it's 1. So that's a 5-fold difference.
Right.
So the surface, it's sucking these molecules. And then you need to provide more through diffusion. So it's just sucking them more effectively. It's consuming them more effectively. Whereas if it would be just 1, the diffusion can go further more easily because it's not consuming so much. So this was something we saw in a joint paper with the University of Helsinki already. It was about iridium films where they used these PillarHall test structures, and that was a little bit a mystery to us. Why when using the same iridium reactant, acetyl acetonate or something it was, and then 3 different non-metal reactants. I think we had there ozone and oxygen and then something. So one of these films grew further than the others, and there was this correlation that actually had a lower growth per cycle, and then it went deeper. And we wrote it also in that paper that we can't really explain why this is. But when you do the modeling and realize that, it just binds those molecules, it consumes them, it's completely logical.
No, that makes loads of sense. As more molecules on the surface, more things to grab something that's coming by. Lower diffusion doesn't get as far.
Yeah, I
think that tracks wonderfully. So growth per cycle, something that we haven't talked so much about in conformality. Our conformality discussions. But then there was also a discussion about how the channel length is changing. Right. So this discussion about what was the term that you used? The half saturated thickness, half
50% penetration depth. I think we used that term. Maybe we need to come up with a better term. Well, just penetration depth, perhaps. But you have to define then more carefully what it means. So that's where the film thickness has reached 50% of the value that it has at the saturated region. This is also something that Markku Ylilammi came up by himself, that this is a significant one, and also Karsten Arts ended up using the same. So that I think should be quite a good definition to look at, where it's 50%. Yeah. So can you repeat or follow up with the question?
Sure.
What was
Yeah. So as you increase or change or get closer to this half penetration depth thickness, then that is changing some aspects of how the molecules are interacting or moving around. In addition, right, based on the type of flow that the molecules are now in.
Yeah, I'm not sure if I fully understand the question, but I think that you are coming to the different flow regimes. So
yes.
So we have the Knudsen diffusion, where the molecules are effectively not meeting other molecules in the gas phase. They are just their mean free path is so long that they are actually hitting the wall before they hit each other. So that's one thing. And then when you start to have a higher pressure or higher gap height, then these molecules start to interact, and that would be then the gas phase diffusion. And these are mathematically described by two different formula. When you are, you are referring to that one figure. Yeah, it's actually difficult to explain. So we made a gap filling experiment with a model. Indeed, it's much easier with a model than with any real test structures. So we made an experiment where we are filling the gap either by growing a thicker film or varying having the same film thickness and varying the gap height. And what happened there was that when we had a narrow gap, we were in the Knudsen diffusion regime. So people call it the free molecular flow as well. That's what we called it in the paper as well. But then when you increase the gap height, meaning that you actually have less of this filling percentage, if you always had the same film thickness, then you start to be in the region where also these gas phase collisions happen, and that affects how deep the film grows. So the most effective one is when there are no gas phase collisions, because, well, you can actually quite easily visualize it. If you're just flying freely, as far as you can, or otherwise you are bumping into a molecule in the gas phase, and that's bouncing some of the molecules back and some further, so that slows down the entry to that channel. So if we have just one single channel which we are filling, then we are not changing the flow regime actually. So I think that was your question, and maybe that was a little bit confusing. So when we are decreasing the gap height, if we already were in the free molecular flow with the Knudsen diffusion, then we are going to remain there because we are still making the gap smaller.
Okay, yes, because you're closing in.
Yes.
Yeah. Interesting. This was something that I thought about a lot when I was reading the paper, just because when I was in grad school, I have a paper about surface smoothing using ALD. So, essentially a very similar type of process that's happening as you're closing in the gap of these PillarHall structures, that you're closing in the gaps of more trenches, just the other way around to try and essentially cut the tops off. So I was thinking, is this something that would have this change in flow regime or something like that, something that would have affected when the surface smoothing is happening as the kind of trenches were changing? But I suppose the conclusion is it would not.
I think not indeed, but then the aspect ratio is getting higher, and that means that your film is not growing as deep. So that's what we were really wanting to show. So we were looking for this, whether we could find some conditions where we could talk about a fingerprint saturation profile or fingerprint thickness profile that is then really like fundamentally representing an ALD process. And we kind of found that, and it's fully in line with what people have done earlier in the literature, that we should be in the free molecular flow regime, so the Knudsen diffusion should prevail, and we should have just a few percentages filled of that gap. So that's actually quite similar as in for example, kinetics thinking in catalysis, where if you want to observe the kinetics, it's best to have low conversions for those reactions. So this is very similar in a way, or different concept.
But before I move on to a discussion on the PillarHall structures, could you just explain or elaborate a little more on what this fingerprint, or like representative ALD film means?
Yes. So actually, I have followed the footsteps of Angel Yanguasgil, I would say.
Okay.
He was very nicely talking, I think it was in Linköping, a conference. Was it the Euros CVD or what was it? Henrik Pedersen was organizing it. He used the word ALD measurable.
Okay.
And he's done a lot of great modeling and also looking at CVD and ALD next to each other. So if in CVD the growth rate is the measurable, that's really fundamentally representing the CVD process at a given conditions, so meaning the temperature and pressure. So then he was using the word ALD measurable, and that was exactly this thickness profile into a high aspect ratio thing. So ALD measurable. I was using that word also in some of the papers, but then we somehow came up with this fingerprint, and I'm sure that somebody else has been using it also as well. So yeah, something that a certain ALD process leaves behind, wherever you apply it. I like the concept, and so you know that for a given process you have a certain growth per cycle, depends on the reactants and the temperature and a little bit on the substrate, but once you are like far enough in the process so that the initial effects of the substrate are gone, then you have the same growth per cycle, right? So that's one thing, but that's not the only thing. So when you work with these high aspect ratio structures, some processes have a really abrupt film. You could see it as a termination profile. Actually, it's the adsorption front. It can be very abrupt, or it can be more shallow. So that's something that's also really fundamentally related to the process, and actually that's where the kinetics part is. So when we talk about reaction rates, those reaction rates affect that. It has been quite difficult to access kinetic information about ALD processes because they are so fast and they are not continuous. They are these, always changing. They are always in a transient state. But when we look at the thickness profile or saturation profile, so how much do we get per cycle and how abruptly do we go to zero? Those are the characteristic things there. I'd really like to have a library of these.
Yes, that sounds like the perfect type of thing to have a library for. Yeah.
Yes, yeah.
Interesting. Yeah, I think it was a unique term for me to see in the paper because maybe just from past spectroscopy experience, I think fingerprint, and then I'm thinking about IR. And,
right.
That's where my brain went, but I think it tracks very easily that there should be a fingerprint.
Yeah.
Or a uniqueness to each ALD process, of course.
So ALD measurable or fingerprint, what's better?
You're really putting me on the spot here. I'm going to have to take a page out of the U.S. court book and say I plead the fifth on this question. Listen, I think I'm asking the questions, right? That's how they is. I'm the one asking the questions here. Hey, but good. So let's move then on to the PillarHall test structures. So these were structures that you were using in this conformality paper, but this is also something that is very closely tied to your own work. So if you could tell us a little bit about where these PillarHall structures came from, how they were conceptualized.
Yeah. Yes, so this goes back to the times when I was working at VTT, and that was after my postdoc at IMEC. So I worked in the Micronova clean room for more than 10 years related to ALD. And in those times, we also had a bigger funding together with the University of Helsinki. That was the Center of Excellence in Atomic Layer Deposition. And that gave some academic freedom to do things that would not be possible we had otherwise Tekes funding, or that's Business Finland. It was more like pre-planned what we did, but this was academically free things to do and to try out. And there we decided to go and make these test structures. Why? Well, that had to do with the ALD work that I had done. So I was the equipment responsible there. By the way, I was there to take the first Picosan tool into use. Now I tell this in a Benec podcast, but yes, that tool was bought to VTT, and they looked for a researcher, and that was me. So I was there with Sven Lindfors taking the first ever Picosan prototype into use. That's gone a long time ago already. I think that at that time Benec did not offer any possibilities for the wafer processing. Of course, now you do a lot. History
is history.
Yes.
So we will not.
But so I was there, the equipment responsible, and we had just simple aluminium oxide, titanium dioxide, and nanolaminates there in use. And by the way, also that we combined these two processes. That's another story altogether, how we ended up in this. But the TMA water and titanium tetrachloride water process, they have been serving really well for a long time. But then, so there, I always had this ALD focus. I was in a MEMS team, so microelectromechanical systems. So actually my colleagues were building these things on wafers which have moving parts, electronically controlled or sensing something and doing really complex stuff. And I was always wondering, how do they manage to do this really properly? And ALD was used in part of some of those processes, sometimes as an etch mask or something, or an insulator or something. And then these requests came like, we have these features in our wafer. Can you put the ALD film on that so that it coats everything? And they could be really demanding things. So then you'd look at the dimensions, and I wasn't able to answer. So what we had, the knowledge that we had, were these vertical trenches.
Sure.
So at Micronova, they also have the capability for this deep reactive ion etching, the Bosch process, I think it's called. And our usual conformality test was that, and we could get these test structures up to about 50:1 aspect ratio.
Okay.
And the ALD processes, all of them went into that really nicely. But then when you get something with 300:1 to coat, how do you answer if you are going to be able to coat that? And can you make tests with real wafers? I mean, if you screw up a wafer, it's thousands of euros worth. So that's where actually came the idea that we need separate test structures for these, so that when these people come in with their question, can you do this? I would be able to either say, either no or test, not with their wafers, but with test wafers. And that's also why then, that's why one reason why I wanted to make these really demanding ones, but then I still have made them more demanding than anybody would have wanted, because I have had this long-term interest in the fundamentals of ALD, and I really wanted to see the differences between all processes. So I have made them so demanding that, you know, with the normal process conditions, no process will ever go to the end. So you can always see the differences.
Okay, that's great.
That was my, yes, I really wanted to push it to the limits, yes. And we had all kinds of ideas in the beginning of some funny structures that we would do. So we actually were imagining this with the VTT colleagues, that we would make a bus route from here, Micronova, to the University of Helsinki Kumpula campus. So we could make that there, but we never ended up doing that. But you could, of course, do anything with this lithography. But what we ended up doing is this really infinitely, to the molecules, an infinitely long trench. It was on the order of 1 centimeter, which is far too long, but it's really, really long. I even actually carry on my back one of these chips. I can show you. Yes. So infinitely long trench, and just with one well-defined gap height, and then also, well, those chips, they have several lengths. So there are the really long ones. I think 5 millimeter is the standard longest membrane, or gap length. It has a membrane on top, and then there are also smaller ones. So in one chip you can actually see many aspect ratios at once.
Okay. Yeah. That's very nice. Yeah, I think the use of it is very, very easy. Like the user interface is so straightforward. I think that it's almost seems like, oh, well, how have these not always been being used all the time?
Yes.
So what is it? It's you just peel off with a piece of tape. Is that right?
Yes.
Yeah.
Yes, indeed. Yeah. So I was designing them for my own use, but also I was thinking that other ALD researchers in the world would want to use them. And indeed, when I introduced them for the first time, I was actually visiting Colorado, I think 2014 or something. Stephen George had a seminar or something where I could give a talk, and then I visited the lab. And when he saw those chips, he asked me right away, "Are you going to make these available?" And I think I answered something like, "I'd like to," but it was a long way.
They are available now. Yes.
They are available, yes. So there is this company called Chipmetrics, led by Mikko Utriainen, So I did this business development part myself at VTT, so I really wanted to push them and make them available, but at some point, of course, your capabilities stop. And I got this Business Finland funding, TUTLI funding, tutkimuksesta liiketoimintaa or something, so business from research. And there you needed to have a business partner. And at first I had somebody else who didn't really believe so much in these. But then I happened to sit in the same room with Mikko for a moment, and I showed these to him, like look what I have here, and I find them interesting. And he found them interesting. He has made his thesis also on ALD in the 90s. Okay. And he kind of got it. And so there I had a person who understood and was interested, and now he has created a company that sells those.
Mikko Rita started...
No, Utriainen. It's
Utriainen.
another
Okay.
Mikko. No, not Ritala. No, they have just, at the University of Helsinki, they've used them a little bit. But I'm happy that Ervin Kessels saw the value. We have actually many joint papers. Good. Great papers with them, where they have been using these for different purposes. So doing exactly those types of things that I imagined that people would want to do with them. So I think that's just the path has been opened, and I hope that a lot follows.
How did you make these? I think it's fun that you're doing this for evaluating some ALD processes for eventual wafer processes. But then these are made from silicon, right? Did you have to make these also on a wafer?
Yes.
So then, okay,
They
so
are
it was
made
like
on wafers. Yes.
a wafer device then to test for then a process to go onto another wafer device. Which
yes.
I think that's fun.
Yes, and with those techniques that were available in this MEMS processing. So it's all these lateral types of things, actually. So these are lateral high aspect ratio test structures, not going into the wafer, but actually on top of the wafer. And this is the types of things that were done in that team where I was. And first there was Feng Gao, who's also the first author of the very first paper that we did. He was doing the processing. I was feeding the ideas, and we were planning together, but he realized them, and then I took it over actually later. So that was the first prototypes, but they didn't function completely well yet, so improvements were made, and I think that I used 2 years of my life to design these. First 1 year to design, and then another year to process, there were then these process engineers, I think that they are called. So there was Meri Partanen, and I'm sorry I don't remember the name of the other person, but his name is thanked in the paper, who then actually, Tuomo Honkaharju must have been, who made the actual clean room processing, but that was in a close collaboration then with me. So there's always this engineer who guides, and there would have been so many mistakes to make, but I consulted my intelligent colleagues, and then there was this one thing called a stupidity control database that another colleague, James Decker, had been updating for years. So there he had been carefully recording like all the mistakes that people have been making. It's a really long document. Like it's actually really complex to do this lithography for many layers and all that. So I was studying that carefully, and I think that saved the whole thing. I would have made many of those mistakes myself if I had not been able to pre-read about them. So great thanks to this SCDB document.
That's amazing. That's something maybe we all need just in our life.
Yes.
I mean, we just always have it in the back of the brain.
Yes.
That tells us, don't do that again. But maybe we all just need a stupidity database.
Yes. But the good thing there was that it also included everybody else's stupidities. So you could, propose your own or somebody else's, and he would then how do you say, curate it so that it was logical to read. I have started something like that in my lab at the moment, but it didn't progress very far yet. But I think it was a great thing to have.
Yes, that's true power of knowledge.
Yes.
There. How are we doing on time?
I think we are using a lot of time.
Yes, we are. Oh my gosh, we are almost at an hour already. That's great.
Are we like halfway with the questions?
Well, I think we've done most of them.
All right.
Yeah, this is going great. I'm having so much fun.
Me too.
Good. Well, okay. So, yeah, I think you spent 2 years of your life saying, getting the design and making these structures. But I was going to say you maybe don't have all of the extra time to do something like that anymore, but you do have time to work on other side projects, as I know. And one of those right now is the open learning site for ALD. Could you tell us a little bit about that?
Yeah, so if we refer to that extra time, well, it hasn't progressed very much in the past year or so. But it exists. It was created when it was 45 years since the filing of the first patent on atomic layer epitaxy. So that's when we had the first November networking event at Aalto that I wanted to create. I think it's a tradition to continue. We have lots of people here working with ALD, and it's good to bring them together, and in Finland in general. And then also the site, when I came to Aalto University as a professor, I have been taking pedagogical courses, and I learned about these, for example, the MOOCs, where then a lot in the world, and there are some US universities that are really advanced in these massive online open courses. And so there's no open teaching on ALD. There's lots of ALD is a new field. It is actually a new field. So I sit on like two chairs or support on two legs. One is ALD and one is catalysis. Catalysis as a field is maybe 200 years old or something, almost. And ALD is what, 50 roughly.
Right.
And I think that a lot of the fundamental work still needs to be done or is being done at the moment. And also talking about the ideal ALD. Many people have really different views of what that means. And so this discussion on the fundamentals, it should be activated, I would say. I've tried to do that a little on the conferences as well. But so the purpose of the site kind of is to collect together information that is solid, that comes from different sources, different types of sources, and that has value year after year after year. So it's not something, there are many great websites that follow the progress of the field. I would want to mention the Bolt engineering site. That's really great effort by Jonas Sundqvist, and then the Atomic Limit site also. Great things. So the focus on this ALD open learning site is quite different. It is really to be like a source of basic information for students and newcomers to the field. And so because it's also vast, if you look at the literature, and there are more than 200 review papers, and like, how do you start? It's meant to help my students. I've also thought that, well, now with the Millennium Technology Prize, there are also journalists who are interested in ALD. There can be school kids who are interested in ALD. So I think that it would be good that there is some introductory site which serves like several types of needs. And I know it was a little bit bold to start it. I gave it a lot of thought. Do I dare to? Who am I to start one? But then I thought, like, Suntola has studied in this university. So he's from TKK, one of the predecessors. And I have written a few review papers that have gotten really a lot of attention. I don't consider myself any kind of a leader of the field. But anyway, I have some status. So I was thinking really, who could start something like that and where could it be started? And then I thought that, well, I think Aalto University, or this ALD open learning of Aalto, and myself, we are not worse choice than somebody else. So then I thought, all right, I'll dare to do that.
I think we will be better off that there is something, even if you are not the one who takes it to its completion or its most modern and comprehensive form. I think having the seed planted is a good start.
Yes.
Any start is good. Just as you say, Zoom is better than nothing to have podcasts on. I think having something already is valuable. So
a seed planted, yes, that's something that I really like. Yes, and I have some hopes that I would build it further. I welcome also others to join. I think that it will not be really worth having many similar sites in the world. We were actually considering whether it should be at Aalto or TU Delft.
Okay.
But then I thought Aalto is better for some of the reasons that were mentioned already. This is really kind of a home of ALD.
So I'm guessing Ruud van Omen has been part of this effort.
Well, yes. We have been discussing this, and TU Delft is actually one of the world leaders in this online teaching. So I've even been in some of their teaching or a course related to this online teaching. Yes,
that's great.
I was visiting Ruud a summer, and I had the opportunity to follow there something. So they would be very advanced, but Aalto is also good, and I think that the location is logical here.
Absolutely. Well, what is included on this site right now?
There's a brief introduction to ALD, and then there are these different sections. There's a section on review articles. There's a section on books. That's actually the only collection of books I think that we have in the world at the moment about ALD. I think nobody has had an overview of these. So I kind of want to create the overview, actually. And then there probably is a link to a collection of theses, doctoral theses on ALD worldwide. I would think that the number is already over 500 at the moment. Yes.
I wonder what number mine is.
You could check whether yours is there. It's a voluntary basis of putting them in. So yeah, we need people to check that their thesis and thesis from their university are there. Then there's also a section of podcasts. So there's a link to this one. Yes. And what else? Then some useful links. Oh yes, then there's also links to videos like teaching on ALD. So there have been quite some recordings of lectures taken at different locations. I also have recorded my lectures at Aalto University, so I share them through that site so that people can access them. There's actually a great series of lectures from, what's the name now? Stanford University.
Stacy Bent?
It's not from her, it's from a postdoc who was there.
Recently?
It's 2-3 years ago. Now I have to apologize. Nathan Ritchie.
Aha, yes.
Nathan Ritchie gave lectures, and he allowed me to upload them to this site. So that's all with permission, and that's actually a great series of lectures. So I want my students also to watch those. Like, where do you find a good teaching about ALD?
Yeah, it's very hard. It is very hard, and even if you go, I think, to YouTube, which I think is most people's, other than Googling, they go to YouTube to maybe find a nice video. There's not that much.
Well, you can find those YouTube videos through this open learning site, and I'm the curator, so I make sure that what I link to there, it's worth it.
What is the process if people wanted to contribute some information, some videos, some books, or
send me an email and let me know. There is no formal process other than that at the moment. There is a questionnaire for feedback. I had a look at it sometimes, and I think nobody had ever given any feedback. So just emailing me is the most simple thing. It's not going to be a flood of information, I think, at the moment.
Well, this brings me then to maybe the last question of the day, and that's how do you see the openness of the ALD community to kind of share information and participate in these kinds of projects? Is it we're very small still for the most part, as you mentioned, it's still a very new field. We're growing, of course, and that's pretty reflected every year by number of new theses, by attendance at the ALD conference, and so on. Do you feel that we're still at a point where everybody is happy to kind of share information and let that flow around globally?
Yeah, so we are talking maybe about open science then, and so I find the ALD community, it's a great one. I like it a lot. We started the history project in 2013, which is a true open science project. Actually, I learned it afterwards that it's really an open science project. We already started it. It was rather easy to gather lots of volunteers to that. We have done that fully openly. So there is some willingness for that. We have solved some questions through that, I think. In general, I think that many people still see open science as open access, which is a really narrow, limited way in my view. I'd like to think more about open data, open code, open teaching, something like this. And there's a lot to do. I'm really happy that there are some who had already shared these videos of the teaching. Right. That's already openness that helps everybody. I think that we are taking our first steps in this open data, open code. I would like to acknowledge Angel Yanguaskil, who is, to my knowledge, the first one who has made his code openly available. He has this Mach-ball code for conformality simulations. Okay. It's not based on the same thing as our code, but it does basically the same things. So that's something that anybody can just download and use. And so we are also going to follow those footsteps and put our code open data. That's also something we are experimenting with. I was looking for a place for a long time, and then I ended up with Zenodo as a proper place to put our data. So we have there some saturation profiles uploaded, and there should be more coming. In general, I think that these are actually difficult questions in a way that the funders would want a lot of open everything, but then the question, how do you actually do it, is left to us to solve. And when we were publishing the very first open data set, I had somebody from Aalto helping, an open science person, and so you have to think of the metadata and everything. And when we did it, this person was telling me, it's you have so much of data, so how to do this? But that was our very first initial trial with a very limited set of data. So I think that many of these people who are promoting the open science things, they don't understand the questions that we are really dealing with. But I think that the attitude is good in the field. We have just discussed also with Mia Mäntymäki from the University of Helsinki that some of the measurements that we'll do together could also be just published as data. I think that that's valuable when you have a saturation profile or a thermogravimetric analysis or something, so that those data points would be available, so that others can replot and derivate and integrate and do whatever tricks they want to do with those. I think that it would make science proceed faster.
I think that would be really nice. I think looking back to when I was doing some things in grad school, I would try and find like a vapor pressure profile of a molecule or something like that. And a lot of these, even just fundamental physical properties of things, are not so easy to find anywhere. You're searching through, decades old paper trying to find something, and then you may not even find a piece. So just these even little items that just make it that much easier to do the work or just even start an experiment. I think is widely valuable.
And another thing is that when you prepare this open data publication, you really need to dive into the metadata. What are all those descriptions that you need to give? And I think that going through that thinking, being forced to really go through that thinking, is making also better science, because there's always the requirement that others should be able to reproduce your work on the basis of the details that you give. But I think that it often happens that people forget, just genuinely forget to report some, or don't think of it. It's not detailed enough in the paper to report. For example, thinking of thermogravimetric analysis, was it done at atmospheric pressure or vacuum? Did you was it a closed system or an open system? It's not often reported.
Well, where did you say again the data was hosted, where people would be able to find it?
Zenodo.org. Okay. It's hosted by CERN.
Okay. In Switzerland.
Yes.
Okay. Great. Okay. Yeah. Well, Riikka, this has been so much fun. I was so happy to have you on again. So thank you for being here, and thank you for booking this awesome studio for us at Aalto. Before we go, is there any place, social media, websites that we can follow your work at? Our listeners can follow you?
Well, I'm in LinkedIn, but not very actively. I am in Twitter. My hashtag, you find me there with the name, and then hashtag is RLPUU. So brief one, where am I otherwise? I also have a profile in YouTube with my name.
Good.
I have a profile in SlideShare. So I've been putting their copies. And I have a blog, actually 2 blogs. One is the Catalysis Professors Open. That's a blog on the Aalto platform. And then there is the ALD History blog also. I update them when I like, so I don't promise any regularity. I take my freedom there, but there's quite some contents there. So I guess that's it.
Okay.
Yes.
Well, we'll put all the links to them down in wherever the descriptions are for all of these platforms. And just thank you again for being here and for participating in this project. It's been really, really wonderful chatting today.
Thank you for creating this podcast. I think that this is really valuable to the whole ALD community.
You're listening to ALD Stories with Benek, the home of ALD. To stay tuned for new episodes, make sure to follow us on Spotify, Google Podcasts, or Apple Podcasts. We hope you enjoyed today's show. Talk to you in the next one.